the analytical model to see what's going to happen. But in reality, there are always human drivers, almost always. So in a nutshell, the simulation is called imitating the behavior of some situation or process. It's based on the dictionary, I guess. It's a suitably analogous situation or apparatus. Typical simulation involves some sort of inputs that hopefully we could observe or possibly estimate, and then run simulation. It could be a black box, hopefully not, and then get the output. There's something we want to evaluate with. This is the typical simulation, and if we do a computer simulation, we use a lot of computer modeling tools, and it's looking at the process of designing a computerized model of a system. So you have components of the system. Maybe we'll get into traffic simulation as having multiple components. We use a computer to speed up the process. And we can conduct experiments with this model. So the value of simulation, especially computer simulation, is that we can have multiple scenarios, and we can evaluate which one is better or worse. We can assess those performances. And by doing so, we understand the behavior of a system, especially for different strategies on the system operations. So the same idea of similar to simulation. The only difference is we have a computerized system and designed for different components. In a nutshell, what we are doing in simulation is that we have multiple components. We'll get into the traffic simulation, but you need to model roadway system, modeling curvature of the roadway, vertical and horizontal curves. You also need to model the control component. You could have a signal, stop sign, you could have a ramp metering. Those are different components. And also different types of vehicles. And they are doing different physical capabilities. Smaller cars can probably go faster than heavy truck at the beginning of the starting up, things like that. So we gotta have these multiple components. And the key is that we are not just interested in simulating each component. We want to know the interactions of these components so that we understand urban transportation system as a whole. Because we as a traffic engineer, we are really interested in performance of the transportation system by having new timing plan or adopting the new bus rapid transit system, BRTs, anything we want to try out. And then it's not just based on single component. It all interacts with every single component we have. So the challenge is that more component we model, it gets more complicated. And each component does have uncertainty in it. And these uncertainties could be propagating bigger and bigger, so you need to have some control. Somebody argues that if you want to have a detailed modeling, you really have to do the tire pressure of your car. And also the pavement surface, is it rough? The roughness of the surface is affecting braking distance and everything. So how much is too much? It depends on modeler as well. And then depends on what you want to know about. So many use cases of simulation, you can think about many things. One thing not here, but if you go to big building, there's multiple elevators. And you might have seen an elevator doing every floor stops, or sometimes this is for even numbers and this is odd numbers. And do you ever wonder which ones are working better? Can we actually do analytical modeling of analysis? Simulation is a lot easier to model. It also depends on arrival patterns, right? If the number of people coming in is almost identical for each floor, does not make much any difference, right? But it depends on the arrival patterns, and you can actually have a number of people and capacity of each elevator. So simulation often give you easy way to evaluate the system and maybe make a recommendation on it as well. So these are common use of simulations. Some genetic usage of simulation is that we want to start with the existing system, you need to make sure that model is replicating current situation. You do not show something what's happening right now with your simulation. You don't gain the trust. You have to show that my simulation is mimicking what's happening. Once you have that trust, and you can sort of extrapolate using the tool to consider what if scenarios. And there's no way to confirm that this is true, right? So people often use something called the validation process. So I have a simulation replicating current situation, and maybe I try something new, and I collect the field data and verify my system actually can do predictions. Then you have more confidence in making other predictions as well. So that's what we usually do. So the calibration is one of the key components. So the benefits of simulation is obviously it's a so-called risk-free. Worst thing happen is that simulation stops in computer. Too bad, but you can rerun. If you are doing real thing, dangerous situations, like autonomous vehicle operations, you want to do it in the field, not a good idea, right? So simulation is the key. Coming to traffic simulation, same thing applies as doing for the traffic applications. And there's different traffic simulations, and we usually define them based on so-called fidelity of modeling of traffic. The fidelity, what I meant is that how detailed do we model simulation. So we have a micro, meso, and macro. Macro is, as you can see here, macro is looking at the regional level. So when you do entire state, level of traffic transportation network, if you are doing each individual vehicle level movement, that's going to be taking too long, and a lot of times we don't need that. When you look at the entire state, what you need is roughly we have new transportation system investment scenarios, adding another roadway versus expanding roadway. So what you are really interested in is that which one could have a relatively better performance. You're not really seeking for exact number of change in travel time. If you want to do that, you need to have a micro level. But if you have a macro level, which is not moving individual vehicle, you are moving them as a flow of cars. So you are moving number of vehicles together using so-called volume density feature type thing. How many cars you have in the road, what would be speed, and you move them together at the same speed. You don't consider interaction of each individual. I mean, you could do that, but then taking too long and it's not cost benefit. And then micro is obviously we want to have a very detailed individual vehicular movement. When do we use this? It's a very small network, number of traffic light controlled intersections. I want to evaluate how much time we have turnover, spillover probabilities. So I run 25 times and I measure how many cases it has a ton of spillover cases. Then I have a rough idea. There might be 10% or 40%. If you have a more than 25, 30%, it's of concern. So you try to find a way to mitigate them. Or adjust the demand somehow. Demand management is another strategy, things like that. So we need to have individual level vehicular movements. Then what is a meso? Obviously, this is in between. One of the criticisms in the macro model is that it's so-called using static assignment. Static assignment means that when you load a number of cars onto the network based on demands of origin destinations, you load a network of vehicle through entire roadway routes. And in reality, they move over time, but they don't. It's a static assignment. You just assume that's going to be steady flow for entire origin to destination route, so which is not realistic. But if you want to see the relative difference of the impact of having different transportation system investment options, that's acceptable. And micro is too much detail, taking too long for even small size of regional level modeling work. So they are adding something called the mesoscopic. They want to move cars as the time goes by. So they use so-called volume density feature. If you are looking at the number of vehicles in a single roadway segment, if you're the only car, it probably moves at the free flow speed. If it's a jam, it gets stuck. So in between, based on density, number of cars, you can estimate the speed of the vehicles. So that's how they move cars along the link, and they get processed. And it's using dynamic way of assigning cars. So MESO model is adopting that dynamic traffic assignment option, and that's more realistic than macro model. But still, they don't consider lane changing in a realistic way. They do consider a little bit, but not in a way of real individual vehicular movements, drivers having different aggressiveness. That's another important calibration parameters. If you are calibrating for maybe Kolkata versus here, and probably drivers in Kolkata is more aggressive, and you want to consider that as well. So that's how we classify traffic simulation models. So again, microscopic simulation model is looking at the individual vehicular level, and each vehicle is a system entity, so you actually model them. The way we do this modeling is so-called time scanning based. So there's a system of a transportation network, and it could be empty at the beginning. And you start generating cars and cars moving into the system. And in reality, cars are moving based on interaction between any pair of vehicles with the control systems. So it's happening in real time. But when we do this, that's taking too long because there's so many events. One's accelerating, I am following the acceleration, the following vehicle is actually decelerating it, I recognize that, I want to start decelerating. These events are so many, and you don't want to simulate for the entire large number of cars. It's good for very small number of systems, like you want to evaluate toll booth, a single toll booth with the system operator and then number of cars are coming. You can probably do the event-based. But this fairly large scale, we do time scan based. So every single time step, it could be a second, it could be 0.1 seconds. You basically update the vehicular status as a system entity. So that's creating the flow of vehicles and somewhat realistic way. The benefit of this is that we can actually get very detailed outputs. So, individual vehicle travel time, individual vehicle delay, queue lengths. I mean, since you are moving individual vehicle, you get as many detailed performance measures you want to. You can actually obtain them. So that's good. So a lot of cases that we do have applications on micro simulation, even for planning level. If you are, again, I mentioned yesterday about high occupancy vehicle lane operation. Unfortunately, with the macro model, you cannot evaluate HOV operations. So you could use a micro level to evaluate certain planning strategies. And obviously, a lot of operations and ITS strategies can be used. Some challenge of using ITS strategies is that legacy microscopic simulation models, they don't have so-called expanding the capability of simulation that's needed for ITS applications. So one of the ITS applications you want to do, I want to do variable speed limit. And how do you implement that? You have to actually change speed limit while running the simulation, and you have to model individual cars sort of complying behaviors. And it's not very common to every single modeling tools. But modern, recent modeling tools actually have something called API, It's called the application programming interface. It's basically allowing you to change components of the simulation entity without giving you the source code. If you give a source code, one can change everything. But they don't want to give out source code. It's a commercial software, but they allow you to change things. So some RTS applications, you need to have an API. It's a fairly common. And again, the benefits are very well known. So it's the same thing. Why simulation? Why we want to use a simulation model? New system, something that's expensive to build. If you can try out maybe closing lane for an hour, you can actually do it in the field. It's not going to have a huge impact. It might have a bad impact, but it's not too much of a risk involved. But if you want to have a new system, I want to build maybe the terminal of the bus system instead of individual bus stops there. So you want to have a huge bus terminal as a complex, and every bus comes in there and then dispatched. And how do you evaluate that? You don't want to build a new one and then see if it's going to work or not. Too expensive. So it's a new systems or new procedure of maybe I want to change the variable message sign locations. This you can probably do, but how do I strategically locate them, and how many do I need to be effective? And that's something you can use a simulation before purchasing a bunch of them and then deploy them and things like that. So new system is expensive, time consuming, real system has a risk. Also, some alternatives, especially under so-called identical conditions. So if you are doing before and after study, I want to test out current situation versus a new timing plan or new operational strategy, and you are doing before and after studies. And there's no way you could have identical condition of before and after. And also your highway is somewhat low volume condition, and you want to see when this highway gets congested and what's going to happen. There's no way you could make that. Maybe some country you can actually make people to travel, but typically it's not easy to accomplish. So simulation can create exactly the same identical conditions. We'll probably do some quick exercise of creating a number of vehicles with the different headway distributions. I mean, if you go out and then look at the number of car arrivals, they maybe arrive a similar number each day of each time of the day, but their inter-arrival times are always different. It's stochastic. I mean, it's impossible to have the same inter-arrival time for same number of cars. But in simulation, you can. So you can try different things. So that's another benefit of having simulation model. And then most of the simulation benefit is that you can run a lot faster than real time, right? I mean, if you are doing real world testing, it's a real time clock, but simulation can speed up, sometimes 10 times faster, even 100 times faster. Obviously, the goal is that we want to look at the system performance without building in real world. And sometimes simulation is not available, very complex, costly, and also evaluate different design alternatives quickly. A lot of complex functions for which closed form or numerical techniques are not available. So if you have actually designing some sort of turbo engine or turbine system for water management, there's an equation to build that kind of system, which is a fairly realistic. And you can control maybe number of inflow of the water is varying over time and how efficient this is. So you can probably do some equations and use Excel to generate variability in water flows and efficiency of the system. But in transportation, it is very difficult to have a closed form equation, in part because of human behavior. If you assume identical human behavior, you might be able to do that, but that's not something we want. So the simulation is needed for something that we don't have a closed form equations or numerical models for doing it. So I have some examples of the simulation. This is a Chicago area. This is a very large network. Chicago has millions of people, and they wanted to model this individual level and try to see the impacts. It could be disaster evacuations, and this obviously needs simulation because you don't want to have a real exercise. Hey, there's a bomb goes off, and we want to see how people are evacuating. Not a good idea. So they use actually supercomputer from Argonne National Lab and massive parallelization of the computing, try to achieve faster computation time, and they actually were able to do that. Have you ever heard about something called the TRAFVU? TRANSIMS. TRAFVU is the efforts to create large-scale micro-level simulation model for regional level. This was started in early 90s with the Los Alamos National Laboratory, known for the nuclear research. They thought the transportation is an easy one. They actually developed something. They modeled the entire Dallas-Fort Worth. And they modeled the Portland, over 2 million people. They actually run in real time as well. Oops. So simulation is a powerful tool. And also, this is a full scale of Chicago area. There's a lot of modeling tool and some URLs that give you more information about it. They actually converted this TRAFVU into better model. That's what they did. ANL is Argonne National Lab. It's a suburban of Chicago area. This is another interesting thing, and if we have time, we might just try out. This is a Java-based system. It's a fairly small program, and there's a bunch of options to simulate. So the purpose of this Java-based simulation is the so-called agent-based modeling. And in case you have a stadium design, which you cannot really change much, and when there's something bad thing happen, it could be a bomb goes off or fire happens, and if you don't do anything, it's going to be a chaos, and everyone will go into the exit, which is a very small number of exits. I mean, compared to people getting in there, taking time, and it could make a huge disaster. So they are trying to find way to provide the sort of guidance. I mean, if you are in the airplane, they have like a red line to find the exit, in a way, and they are considering many different options. And one of the options is that, is it going to be better to use the ground level so people can run over the ground and find the exit on the other side? Is it safe to jump out of the fence? Is another interesting thing. So they can try many different things, and also the behavior components. People are trying to find the nearest exit, or if I am in the middle and then there's a nearest exit getting really filled up, you might be better off going into further away, and then the less congested exit. So they are giving different behavior scenarios and others. Again, you control everything, but we do model this kind of agent-based modeling based on fairly simple agent behavior logic. And they could come out as a so-called emergent behavior, something we did not expect, having this effect of the multiple agents playing different way. And this obviously comes from military exercise. They are playing the war games, and how do they deploy the military forces, and we borrow those ideas to this kind of applications. Again, there are no right answers, but giving you some sort of estimate that without doing this, you just have a number, ballpark number that out of no foundation, but this will give us something, and then we start negotiating, discussing the ways of estimating. So it gives different steps, and then number of injured peoples, and number of trampled peoples, and how many got exited, based on simple strategies. And this is becoming very popular, especially with the subway, metro line, because a lot of people are in there, and then how they can exit and enter safely, and things like that. So, why we are doing this kind of simulations? The first reason is obviously analytical approach is not available. If you can think about analytical approach in the context of maybe traffic light controlled intersection. The highway capacity manual, we'll probably talk about later, there's the equation to estimate delay. That's just looking at the average, right? But the highway capacity manual, over the time, they recognize the limitation of not considering stochastic variability. I mentioned about there's a left-hand bay that can actually hold maybe 5 cars or 10 cars, whatever you have it there. And when there's a demand exceeds that storage capacity because of the wait time is longer, then it has a spillover problem. And no equation can model that properly. So analytically, if you want to model it, it has to have an infinite storage capacity. That's how they solve it as a queuing system. You can do it, but realistically it's not. So the simulation is a very helpful, useful tool to recognize those limitations and overcome. Again, the key is no risk involved. You can do anything you want to do, and then no one get hurt. And then new situation that's not out there, simulation can do it. And then this is another important thing. When simulation is doing a lot of different aspects of it, you call it like an experimental design. You consider what is the most important factors affecting the performance. This is commonly used for designing drug experiments. Is this going to be effective for young people, elderly people, male, female, pregnant woman or not? They actually have a very careful design of experiments and make sure that their drug is effective in certain target. And they might change the dosage as well. So we borrow those ideas into simulation, and we can try out maybe in signal timing design, is a cycle most important factor, or is turning movement sequence is the most important factor. You can try all different designs, and if you know the ANOVA type statistical analysis, it can give you this is the most important factor explaining these performance measure changes. So that's possible to look at, because you cannot really do this in real world. You have only limited number of observations, and you cannot really field all possible combinations. And you can see the dynamics of the system, again, faster than real time, as I mentioned. Obviously, there are some advantages, disadvantages. I call it calibration. A lot of the public hearings, at least in the US, when the developer comes into the public hearing place and show that simulation or 3D animation showing that if we build a new stadium here, this is what's going to look like in transportation system. So people are excited about seeing new changes and nice animations. And somebody might ask, do you have one for current situations? They usually don't have one. They don't care. But if they show something and it's not reflecting real world, and they cannot really sell their simulation. So it's important to have a calibration for current conditions. And this is difficult and also very time consuming. Difficult in a way of collecting more data, and efforts of doing this is a very, very important, but it's again time consuming and costly. And sometimes some of the variables are impossible to collect, so-called car following behavior. So you can consider car following model as a black box. You can use a deep neural network to model car following model. that you don't have insights of how that's happening. And some of the simulation tools actually require car following model parameters, and it's not easy to observe, and you'll have to tweak them around. I start from default and change this direction and that direction. Is it getting close to the real world situation or not? It's impossible to know exactly what it is. And some of the systems still maintain black box. So black box is something that you cannot really figure it out. And most time garbage in, garbage out actually happens. So you'll have to make sure that you have good quality data, and your good quality data has an output that you want to make sure that your parameters of the calibrations are well tuned, optimized, so that you get the proper output that you have seen in the field. So doing this is very difficult. This is a fairly old document, but I want to emphasize that even the basic science recognize the importance of a simulation. Especially looking at some details of brain activities, and right now they are learning a lot from MRIs and fMRIs, if you know the medical field. Still, they cannot really do the experiments yet. Unfortunately, the human brain, you cannot do any experiments with the human being live. So they are trying to do a simulation on this based on what they learned from MRIs, and try to fill the gap. And that's a very challenging task, in part because a human brain has 10 to the 23 neurons. And no supercomputer has that many power of processing them real time. So that's a huge challenge. That's one big challenge scientists are trying to figure out. You might have heard about quantum computing. You might have a solution to it. I'm not going to spend too much time about this NSF documentations, but their key component is that having simulation is a very, very strong tool to evaluate and understand the component of the system, and it's a must-have, because before you actually do the experiment with the real component or live tissue or system of transportation, simulation can help a lot to reduce errors, and you can have a model that's well sort of evaluated, and then go to the limited access field lab environment, and it may not work perfectly, and you learn from that and coming back and do a lot of more simulations. So in any context of processing the entire system, simulation is very powerful. Even for making a car, they use a lot of simulation for crash testing. It's the finite element method-based FM model. They actually change the different components and everything. So simulation is very important, even for science as well. Again, I mentioned about challenge in this verification, calibration, and validation. These context is slightly different by different textbooks. But my point of view, verification is you check each component of the simulation system, and they actually do what they intend to work. So if you have a system of traffic signal control logic, it should work just like the actual controller does. At least you should be able to mimic them. And if you have cars having different range of acceleration, deceleration range, you should have those being processed. One of the limitations in the modeling tools is that they can actually accelerate reasonably well, and a lot of times their deceleration could be unrealistically high, and they can stop. They don't follow physics. It happens in some simulation tools, and their argument is that our models are not designed for vehicular dynamics model. We are mostly interested in maneuvers of cars accelerating and looking at the performance of mobilities. If you trust them, yeah, that's the one purpose they can argue. And calibration, in my opinion, is that there are parameters that can actually make a different performance in the simulation model. So you tweak those parameters, and make sure that your simulation output is mimicking in the current condition, existing system. That's a calibration. And validation is something that you have not tried during the calibration, the condition that was not used for calibration, something new. So something new that's a validating that it can work with some new untried environment. So the most ideal option is that you want to do something new trial in the field and see the impact of those, and then you use your calibrated model and then run with the changed environment, and then see the simulation model output is providing statistically identical results of the new untried condition of the implementation, if that makes sense. So again, different textbook has a different way of describing it, but that's my definition. So the verification is usually done by the model developer. They need to make sure. But sometimes they didn't do well, and then you need to verify as well. Calibration validation is something we as a traffic modeler do a lot of these. Another interesting component is that if you are doing microscopic simulation, one of the common challenges is when you start the simulation, network is empty. You have an entire corridor or entire network of transportation system, and then cars are being generated from the entrance to the network. We don't generate cars inside, typically. So it's empty, and if you start collecting travel time data, which is not realistic. So you need to make sure that when we start collecting data for measuring performance of the transportation system, you need to identify this is my equilibrium condition or mimicking real world situations. And this is not trivial, because when you have congested conditions, and as you make more cars and then they go into the system, it gets worse every time you simulate. So how do we define this is a beginning of a real world situation? So I'm interested in peak hours of maybe 5 to 7 p.m. And how do I define situation of 5 p.m. so I can collect 2 hours of data? A lot of the ways of doing that is obviously you exclude some portion of time from the simulation run to make sure that when you start collecting data that's similar to the network that you have in the field. That's something you can do. A rule of thumb people usually accept is that when you have a network and the longest entrance to the exit, at least the one vehicle actually enters and then exit to the longest exit. If you actually have that situation, that could be okay to start collecting data, because the cars are filled with the network. Sometimes the people wanted to take a snapshot of a real world and use that situation as my initial condition. So the benefit of doing that is every time you run simulation, you start with the same initial conditions, which is a good or bad, because it's a good to have identical way of evaluating it. Bad in a sense, tomorrow you go there, you don't get the same initial condition. So you could have some biased initial condition as well. And the other option is if you have non-oversaturated conditions, undersaturated conditions, you look at the number of vehicles going in and number of vehicles going out, and you look at the balance. So at the beginning, more cars are going in every interval. And if you see the number of vehicles coming out is similar, and you claim that this is a stable condition, I'm going to start collecting data. So there's actually big research about how to initialize the modeling work. And again, there's no right answers as long as you can justify. So I have an example. CORSIM is a legacy model of system, and they look at the in and outs. So they measure those. And then in VISIM, you have to specify when to begin collecting data. So you can probably roughly estimate from the entrance to the longest routes of the network. It's going to taking probably, with the reasonable traffic, taking about 2 minutes. And I'm going to decide 2 minutes as initial condition and start collecting data. So that's everything about simulation model. I'm going to do a little bit more because later we have a lot more contents. But any questions so far you have? Yes?
Can we use TI for simulation?
What's a TI?
Traffic impact assessment.
Traffic impact assessment. Sure. That's what we want to use the simulation for. So whatever impact you want to have, it could be emissions, it could be total delay, fuel consumption.
Suppose I have a housing scheme and in a particular plot, it's a big housing scheme, suppose 2,000 to 3,000 housing units.
Okay.
And I have to do the assessment, what impact will happen on my junction or road. Can we do that?
So what kind of measures are you looking at?
Delay or queuing lane.
Why do you think it's not possible? So it's a microscopic simulation from 2,000 households. You actually have a number of cars in that complex, and you can probably have a good estimate of where they are going. And then if you can simulate them, and every 0.1 second you actually move the cars, and you will have impact of delays and queue length.
Yes.
That makes sense? Okay. Any other questions?
Is there any percentage range of precision so that as a modeler we can say that our model is actually mimicking the real scenario?
Yes and no. So the planners are very generous about, it's called a GEH, I believe. It's about 30% within the range of the difference, they seem okay with it. But if you are doing different performance, you'll have to justify why this amount of the difference is acceptable. And this is a function of variability and the number of runs you make. Maybe we'll talk about it in more detail later. And the other aspects of the thing is that if you are doing maybe delay at the intersection level, one easy argument is that I'm going to consider level of service A range as a similar. Because the level of service A is up to 10 seconds per vehicle. So if you have a 2-second delay versus a 9-second delay, even though it's a 7-second delay difference, it's a still good A level. And that's some justification you can use. If you want to argue about percentage of the difference is acceptable, then you'll have to have a so-called tolerance level. So when you're looking at the speed of difference in statistics, so you have a radar gun and measure the speed average of 72.3 miles per hour. Do you care 72 versus 72.2? Probably not. Do we care 72, 72, 73? Maybe. Do we care 65 to 72? Yes. So there gotta be, depends on what you are trying to measure and argue about the difference. And then also the variability that you have from the field. So field has a speed of variability from 65 to 72, and your model shows in the range that's probably acceptable, right? I don't know if I gave you an answer to, you probably want to have an X% number to use, but unfortunately there is no right answer to that. Okay. Moving on to calibration. So this might be fun. We'll probably stop at 11. So I mentioned calibration and validation, so I can easily skip this one. In traffic simulation model, same thing. The way I see the calibration aspects is that if you ever use the VISM or CORSIM or Paramix or Aimson, a lot of people actually take a default as a good calibration. So people use a default that vendor thinks that this is a reasonable values. And when they have to make a change, so they collect the data from the field and then enter everything they can enter and run the model, and they don't see the expected results. And now they kind of worried, what's wrong with this model? It could be the data collection was not done properly, or the performance measure from the field is not in the range of the average. It could be one extreme case. So they begin tweaking parameters, so-called engineering judgment. And sometimes they do this without scientific way of changing it. And this is typically, it's a funny, engineers are not getting a lot of dollars for calibrating simulation model. Companies are not thinking that as a really important task. So they don't have a manpower and then hours of man hours to work on it. So limitations on time and cost, and then they don't really have how to do it yet. So this issue will have, obviously, no single model is perfect for real field. It may be good for one condition, and vendor might have collected data from their own backyard and then did a lot of efforts of calibrating it. But if that goes into other country or other locations, it doesn't work usually. So if you do have a manual adjustment, it could be unrealistic and sometimes erroneous calibration results. In part because you don't know the data you have from the field is representative of a field average. And field could have large variabilities. And you collect the data for short term, and that's a sort of extreme case, and you are not getting the right results. And then also an uncalibrated model could have misleading the results. So better to use a procedure to calibrate. So I'm going to show you what happens if you do not use a well-calibrated model. So this is a real-world case. So this is the field travel time that we collected from about 11 signalized intersections, a fairly big corridor. And it takes about 600 seconds to travel. And we actually match the license plate, so we are getting travel time from one location to the other. So this is a histogram of that travel time. So some actually getting fairly low travel time, and some are getting longer travel time. And this is so-called a bimodal distribution. It's not like a single mode of normal distribution. And guess whether this makes sense or not? To me, it made a sense because the way they have a coordination, this is the longest storage capacity in this corridor. This is so long, and they could not make a single progression, meaning that vehicle stopped at the red and beginning to get in green, they cannot get through entire corridor. If you do that, the bandwidth is so small, only one or maybe half vehicle can make it. So they are creating huge storage that everybody get the progress up to that point. They stop here once, they're making another progression over there. And then some portion of cars are getting through without stopping. And majority is stopping again. So this is making difference. So we thought this makes sense. So this is the field data. So field data does not lie, unless we have a biased sample. So we got actually fairly large data samples. So with this data, we use the uncalibrated model, which means that whatever the vendor actually shipped with the default settings. And we are comparing the field condition of these. This is a field condition, right? And this is what model shows. So there's a huge gap. It's obviously possible, right? And we actually used calibrated model. And here, I'll have to be honest, that they look similar in a way of average travel time, but they are not creating exact bimodal distributions. So I'm not sure, but this is as close as we can get. But there is some portion showing that maybe bimodal distributions here slightly different. But this could be, again, field is only one day, and simulation could be slightly different. But this is what we got, and we are happy about this. Let's say this is a calibrated model, and then we are evaluating this with 3 different timing plans. So this is a timing plan. Let me just show everything here. Timing plan from synchro program and 27F. So this is a base case of the field setting. So field has a timing plan running, and based on this one, what it shows is that synchro is the best performing timing plan in terms of travel time, right? And then next is the current, and 27F is worse. And when we showed this one to the traffic operators, and they actually optimized the timing plan using synchro. And their timing plan was not old. They were less than a few months. So the current and the synchro should be very similar. So amazingly, when you used our calibrated model, the current and synchro were almost identical. And there's a small difference, but it's not huge difference. And then 27F is not that good. So this is kind of indicating when you actually use default settings, and you may not be able to make right decisions. So it's the importance of the simulation calibration is sort of given. And then you will have to study what to calibrate. One of the principles is that when you collect the data, you should be able to collect the same data from the field. Then you can actually make a comparison and see if that makes sense. So stop delay is something commonly used in the highway capacity manual. And the field, how do you define stop delay? And in the simulation, they have different ways of defining stop delay. In the VSIM, you can define whatever you want to do. CORSIM used to actually define stop delay as a complete stop. And then also they add speed is below certain level. I forgot, 1 meter per second or less, then you take half of that time as a stop delay. So it's 2 different ways of collecting data is not good. So make sure that the data you collect from field is identical in simulation model how they calculate. And then some critical output model is important to consider. You don't want to use a number of vehicles in and out as a key calibration parameter. Unless you have oversaturated, everybody goes in, they come out. So it's not really a good indicator. But people show that number of vehicles as an indicator for calibration, which I don't think is very convincing. Some of the parameters, mostly driving behavior parameters are key component because number of cars going in is pretty much the same. You cannot really lie about it. Arrival distribution is one of the key challenge. So we can mimic them. Is it random arrival? Is it following Poisson? Is it following platooning arrivals and things like that? And then there's differences. That's mostly because of drivers' behaviors. You might have heard about platooning dispersion model, platoon dispersion model. Robertson's platoon dispersion model. That kind of mimics people when they start from the upstream as a platoon of a saturated flow, and they usually don't travel like a train. They spread out. And this is because some people want to go faster than others. Some people don't want to go fast, and they're creating those fluctuations and then changing the proportion of the progression of the cars are changing over time. So some of the parameters are because of lane changing behavior. I personally do make a lane change if you want to go faster than slowly moving cars. Some people, I'm just good, right? So that's one component. And then my desired speed is not over 10 miles per hour of speed limit. So I see 45, I usually go 50, 52. Some people might be going 55. Some people even going above 15 miles per hour speed limit. So their desired speed are different. That will create a lot of the lane changes and other behaviors. And then how closely they are following the vehicle. I hate people cutting in front of me, so I try to maintain shorter headway, reasonably shorter headway, not like a crazy shorter headway. Some people are okay having longer headways. So these are all components that we can calibrate, and that's going to affect on the performance, entire travel time, queue length, things like that. And then a lot of parameters are available, and depending on simulation model, they have a gap, headway, desired speed, acceleration rate. Parameters are changeable as well. So this is an example of having simulation model calibration example, which I'm going to do in another 15 minutes. Any questions about this calibration issue? Okay. Let's come back 11:15, your clock. That one is going faster by 5 minutes.
It's 11.
Yeah, it's 11. Okay, thank you. And validation, we call it. Let's see how we did it. Nice picture. Chicago downtown area. So we actually studied the Chicago downtown area. We were looking at the north side of Chicago area, and we used the CORSIM model, and we collected the data for CORSIM to run. And this is a sort of a network that we dealt with it. And if you know the O'Hare Airport, and that is the northwest side of it, and you drive probably 40 minutes and you come to the downtown Chicago, the Loop area. And a lot of cars are getting off from Ohio, which is a connection to the interstate highway. They come out and then go into the downtown. And also a lot of cars actually going to the freeway through Ontario, this area. Don't know if you can see them here or not. So, and then there's a couple of intersections. So we collected about 12 intersections of data and tried to calibrate. And it's not an easy task. It's probably very extensive data collections that we have collected. Not many people have done this. So we want to calibrate CORSIM for baseline, which is existing conditions. And then to validate, we designed a new timing plan. And then we implement the timing plan, and then we compare what we call the calibrated CORSIM, predicting the new timing plan, and also we collected another data from the field. So we are making apple-to-apple comparisons. So that's how we did calibration and validations. So start with the calibration context. The context is important. What are we dealing with it? What is the important measure that we call it as argue of calibration and validation? So in this case, number of vehicles is not very relevant. We are looking at the delays and other things. And then also, how do we collect the data? And then when we have a data, even data has uncertainty. If we only collect the 1 day, can we trust that this to be close to average? And also, model has a lot of uncertainties. And how do we quantify these uncertainties? And then also provide a feedback to how we actually do model usage. Model is obviously not perfect. I can give you some examples later on and how we actually made that to be somewhat realistic. And also the validation requires predicting performance under new or untried conditions. So this is how we actually did it. Some questions that we want to ask is that how well can this CORSIM reproduce field conditions? So how well is how you define the well. And then CORSIM can be trusted for new, untried conditions. But that's the ultimate use of a simulation model. I want to calibrate for base case, and I want to try different what-if scenarios. And I want to trust that prediction that I'm making using calibrated model. So this is a key questions we are asking. So CORSIM has a viewer, the TRAFVU, and then you can see a very detailed level. And this is a network we actually coded entire, not entire downtown, about 12 intersections as a key, and then added other intersections to generate external vehicles arrivals. So the way we have it done, we collected data in May, and then based on the data, we calibrated and we developed a new timing in August. So we did it over summer, 3 months. And then we implemented this. We had to show simulation results to the chief of the Chicago Department of Transportation. Are you comfortable us to implement this timing plan? This is risky for them. And then we did it over a few days, and then we collected new data on September. So this is how we did it. We collected data for PMs and AM peak periods for the major entry nodes. And then we didn't have enough manpower, so we actually collected the data, some of the minor intersections as a floating 20 minutes. So this is the assumption. We collected data for 20 minutes. Those turning percentages are going to be similar to entire hour or 2 hours. And then we actually had a video recording of internal intersections. The reason we had used the video was to make sure that we can get the queue length and stop delays, whatever we want to measure, using something that we can go back and then double check. So this is estimating the arrival, which is a lambda distribution as well. So this is a simple estimation of how many cars are arrivals and what kind of distributions it has. And then we also use turning percentages and vehicle mix. There's some heavy vehicles and buses and others. So we use the proportions. And others we were not able to change at this point. So we just use those as the default settings. Some of the issues was we hired students from University of Illinois at Chicago. And obviously some of the students are not really diligently counting cars. They were just counting cars, whatever they want to do. So some unreliable counts. And we are trying to use the internal counts, and then we can actually backpropagate to the external node, and we adjusted it. And some of the source of manual counts for verifications. So we have a downstream intersection counts are fully verifiable with the videos, and we were able to adjust to that. I think that this is an example. So we had actually video counts. So this is, video counts. So this is 100%, almost 100% accurate. And then we had manual counts of these, which is fairly reliable on this case. And then these are not matching. So these, based on these gains and losses, we are able to adjust these parameters. It's not happening everywhere. There's 1 or 2 places that we had overtrusted that graduate student. So it happens. And there is no way to verify this is the right thing or not, unfortunately. We had to make that assumption. And also we were very interested in about the counts of the fluctuation over 2 cycles. And when we had manual counts that we actually estimated as external arrivals, and when VISM, this is CORSIM, sorry, video counts and manual counts should have a similar variations. And obviously there's a slight time difference between internals and an external location. But this is every 2 cycles we are comparing it. And there's some fluctuations, but in general they are fairly similar. This could be due to some of the cars that are going into the garage and coming out of garage as well in downtown Chicago. But in general, it's showing similar fluctuations. So CORSIM inputs are very obvious. We know we have to enter how many cars are coming in, what percentage is at each intersection, and what is the vehicle mix, heavy vehicle percentage, and so forth. And then we have signal settings we got from the Chicago Department of Transportation, and then geometry conditions, and then again other parameters are kept at default. Here's the challenge. So a lot of illegal parkings. If you are ever, how many Starbucks do you have here? Do you have a Starbucks? None? Do you know what Starbucks is? Oh, okay, okay. I was just trying to make sure. So in downtown Chicago, Starbucks is at every other corner. Or there's another bakery shop, and people are illegally parking in the morning and getting their coffee and then maybe bagel or pastry. So it's happening. And police is not enforcing them. They are voters, so they don't want to have trouble. So illegal parking was a big challenge, and this we were able to fix it. And another unfixable challenge was so-called lane utilization. Maybe this is not happening in India. In the U.S., public bus is not that many, probably a few per hour, and no one follows the bus. Because you know that's going to stop in fairly soon, and I don't want to get stuck. So it's called like an empty syndrome on that lane. No one follows the bus unless they are ready to change lane. So this one we are not able to fix. This is something we require to go into the simulation tool and change. We are not able to do. But at least we were able to change this illegal parking scenario. So the way we have done was whenever there's illegal parking, we are creating sort of lane blockage. So people are not able to use the lane because of illegal parking. So this is the right-hand side of driving. I know it's confusing. So they are traveling, but here's a coffee shop, and this lane is not usable. So we actually block them. So they can actually travel, even though it's 3 lanes, they are only using 2 lanes, and then they can use the 3 lanes again later. So this was okay to mimic illegal parkings happening in downtown Chicago. So that was okay. Again, the other challenge was special lane utilization. So this area is not separate 2 segments. It's a single lane with a 4 lane going, but they have a 2 lane going straight and 2 lane going into the highway. And in reality, maybe people in Chicago, they don't do change lanes going like this or going like this. They don't. They actually set aside which lane they are going to be, and they don't have illegal lane changes. In CORSIM, happening a lot. So we actually separate them into 2 different links, and then we are able to fix it. There might be 1 out of every 1,000 cars and try to do the lane change, but which is not very common. Unless they didn't know how to drive and then change. Most people know how to drive this area very well. At least this is going the simultaneous screens, which is not causing a lot of trouble. So we will have to fix that one. The calibration parameters, we use the throughput, performance measures, and then congestion measures of stop delay. Again, the challenge on stop delay had some discrepancies, but we were able to use. One thing we actually did here, unlike others have done, is the so-called looking at the percentiles. So a lot of people actually use a simulation and then create an animation once and then see if that's reasonable or not. You never know that animation is in the percentile-wise, middle or 99th percentile or 2 percentile. So we actually create 100 runs and make sure that we are looking at not the extreme ones, median and then 20th percentile and 80th percentile in terms of queue time. So we are actually looking at the different perspective of the situations. This is more like you are observing 100 days and you are looking at the worst, maybe 80th, median, and then 20th, and see if this makes sense. So that was kind of something we tried and seems working okay. And this is what we are showing. Here are the interesting findings. we thought the throughput should be very, very much identical. And we found a lot of discrepancies. So you can see here about almost 500 cars in the morning. And this was, we figured out that this was so-called the garage effect. If you are actually going into the Chicago or New York, there's something called the early bird, and if you can go in before a certain time, you get cheaper parking rate. And also there's a monthly parking permit holders. They usually go into the downtown area and the park and then move. This was pretty much what we can get from the field. And then in CORSIM, there's not much discrepancies because in CORSIM, we did not model garage. Maybe we should have, but we did not collect the data. So we were able to just knew this is the reason, and then we just assumed that these impacts are not that significant. Again, throughput on the key links. What we are looking at is that in the field, we only had a one-day data collection. And we have no way knowing this is what percentile of the counts for entire 100 days or whatever durations. But CORSIM, we can make multiple runs. So we made 100 runs and then looking at this average and then measure the standard deviations. So if you look at these numbers, and a lot of times you have 1.96 standard deviation, that's a 95 percentile. So if you multiply this plus minus 1.96 standard deviation, the counts are very, very reasonable. So we kind of felt that, except for a few garage effects, this seems okay with it. And there's some challenge. So we used the throughput on certain locations. This is a somewhat extreme case. So the distribution I'm showing is what CORSIM generates. CORSIM can generate 100 times of simulation. That's like 100 days. And we can create a histogram, which is this histogram here. And then field on that day was here. So was the field also extremely large? We don't know. Field could have been this, could have been this, could have been this. But we'll have to compare in multiple locations, see if these are in the range that we can see so-called the plausible conditions. So this was one extreme case of not doing good. Sometimes it's reasonably doing well. Sometimes it's on the other side. This is stop delay. So stop delays are showing the different ways as well. So some are good or bad. Whether this is acceptable or not, it's debatable. So what we did was, this is variations of the flows we have seen in the number of cars. And CORSIM is generating a reasonably larger variation in number of vehicles coming in. We thought the CORSIM may not be able to create large fluctuation of the volume per 2 cycles. And it's fairly similar to field. That was good. We were looking at the new timing plan. We actually only optimized for offsets. Do you know what offset is? Okay. So offset is for the progression. When the intersection here starts green here, and then how long does it take to have another green start here? So in a sense, if I can change the color or not, maybe. So if you are stopping here as if you come in here, and then you start moving, and if depends on when green starts. If green is starting right there, then you can actually go through. So this difference between this green time and this green time is offset. And if green starts later, then they have to wait until they have new green comes up. So depending on the offset value, you will have a progression of the vehicles. Do you see this? This is a sort of a trajectory. This is a time. This is distance. So the slope is the speed. So depending on the slope of the speed, you can actually hit the green again and again. That's offset. So we are optimizing offsets for 21 locations of the intersections. This was where I worked for, and this is City actually saw the animations and they seemed acceptable about implementing this. So this was a huge challenge for us. I mean, it's just scary to implement something we have not really fully tested and confident about it. We used the simulation, we calibrated, but it was scary. So this is what we actually did, and this is the so-called prediction versus the reality. So the prediction is what we actually got from CORSIM. Again, in CORSIM, we can make multiple runs, new timing plan, new offsets. We expect that this is the range of the stop delay per vehicle, and then we collected the data after we implemented it, and this is what field is showing. So this one's a reasonably very good prediction. This one's not as good as what we thought, expected. Here's how we actually justify. Again, when you actually do a research, it's very important to argue something that people can nodding on it. And we argue that this is reasonably good, not the best, but acceptable. So CORSIM may not be perfect to estimate absolute performance measures. We want to show here is that when we compare before and after of our real field and CORSIM data for two different timing plans, are they showing into the same directions? So delta difference of CORSIM versus the delta difference of reality. So there's 5 locations we had extensive data collections and data. So the delta is September versus May. September is the new timing plan, and May is original timing plan. So some places it's showing that very similar challenge ranges. So it's showing clearly that we are doing very similar on Ohio at LaSalle, and September is a lot smaller. So it means it's a huge improvement in southbound LaSalle and also northbound LaSalle, and then it gets worse on New Orleans freeway, but similar on this Ontario. So the key corridor in this area is LaSalle Street. I can go back and show you. Maybe I can go back and show you that that's the LaSalle. So this is the LaSalle Street. This is only two-way street in this downtown area. This carries the most traffic because the others are all single two-lane one-way streets. So this is a key corridor for connecting downtown Chicago to north of the Chicago area. So we were making huge improvements in this one. It means that delays are very much reduced due to the optimization of timing plans. So this is just showing that delta difference of between CORSIM and then realities are very much matching. So we argue that maybe CORSIM is not a perfect tool to calibrate and validate, but at least we actually had efforts of calibration and validations, and we can trust the doing the predictions of a new timing plan, just showing the same as the field conditions. Again, field is only one observation, so it's very difficult to argue that field and then CORSIM predictions are exactly the same. And also, this is showing the different locations of the conditions. So field is for the September field, and this is what we are showing. May field, they are showing similar. So the conclusion was that CORSIM is imperfect but effective, and we had a sort of ultimate validation. Chief of Traffic Operations actually used this corridor as his commute, and he was very happy about that corridor. So it was good. The point I'm making here is that calibration is not an easy effort, and this was probably one of the big efforts of collecting massive amount of data. This is all done manually, video recordings and others, and try to demonstrate that simulation model can be calibrated. A lot of people do not calibrate. They feel that just too much is impossible, but we wanted to show that something can be done and make sure that that's acceptable by the traffic engineers and also the modelers. One thing I want to emphasize is that when you use your simulation, you actually control everything. So you got to have your own confidence that this model is trustworthy. It's a replicating field conditions in some level. May not be perfect, but it has to be, you have to have your own confidence to sell to others, which is important. This is going to be in the afternoon, but there's a lot of materials, so I'm going to go ahead and then give some discussions. I mentioned about a lot of materials. This is one of them, Traffic Analysis Toolbox. This is efforts given by Federal Highway Administrations. They have probably 10, 11 volumes of these. Their goal was simulation is important, but a lot of engineers are not comfortable using simulation modeling tools. They, especially if they work for state government, local government, they usually hire a consultant and give the contract and then have them work on it. Unfortunately, when consultant came back with the results, they don't know how to evaluate. They don't have any engineering background to assess how good the modeling efforts were. And also, because the modelers are working at the consulting firms, they don't know how to calibrate, how to model well, so their models are not done well. So in that aspect, they have done these volumes and try to educate engineers and practitioners and state employees gaining knowledge about the modeling tools. So this is one volume, how to select the modeling tools. If you know the modeling, this may not be necessary to go through this exercise, but if you are need to educate your boss, or if you are new to the modeling, and this might be helpful to understand the insights of how to select a model. And at one point you'll be probably nodding, okay, that makes sense. I think that's important. When you use a model, people just simply input the model and run and get the data and happy about it. And if you know the modeling aspects of the details, and if you have results and that you can probably tell this makes sense, this is not making sense, something is wrong, and you could even speculate something in this aspect is wrong. That's how you become expert in modeling. So understanding the behind of the engine is important. A lot of tools are available, sketch planning, which is a very, very high level, demand models, analytical way of doing, like HCM is an analytical model, timing optimization tools. They are doing more macro level than macroscopic simulation models sometimes, and the macro model, meso model, and micro models. And how do we select these tools? It depends on the context. Are you doing planning level? As I mentioned, when you do the planning model, you use a macro level tool typically. European countries are adopting mesoscopic model for planning analysis. They realize it's important to model at least the dynamic traffic assignment. Static assignment is so unrealistic, so they actually switched to meso level to planning level. So it's changing over time as well. And also, computation power is actually supporting that kind of a switch as well. And at some point, we might be able to doing micro model for entire city. That's a sort of trend seems they actually did it. Design and operation and construction aspects, you have different modeling needs for it. And also these 7 categories. What is your study area? What facility do you want? What kind of modes of travel you want? What kind of strategy you want to evaluate? And you really have to have a response to from travelers. Are you providing route guidance systems? Are you looking at the diversion from the drivers on the variable message signs, and what performance measure you want, and what operational characteristics you are looking for in terms of benefit cost analysis? So these are all the questions you might want to have when you select modeling tools. For the macro models, you cannot really get the individual vehicular variations. You don't really do the route guidance system with it. If you want to look at the fuel consumptions and emissions data, you really need to model individual vehicle and their accelerations and speed changes. So then you can actually eliminate what models are necessary. This might be very simple for modeling experts, but if you are totally new to this, you probably need to have some sort of screening process to find the right tools. So this is going into very detailed level. I'm not going to read this. It's a good material to look at, and also available as that guidebook, the traffic analysis toolbox. It's freely available. You can Google it. You should be able to download it. A lot of the aspects of these is what we look at the context. Again, the planning level that you don't really do the microscopic simulation that kind of tells you that if you want to do the operational and construction levels, sketch level, demand models are not available, so it's kind of give you sort of high level that which model might be more applicable, or at least applicable to consider. And this is the sort of categories for selecting. This is an Excel-based worksheet, and you can actually download from your computer, and we'll probably do have a quick exercise of doing this. And this is again the tool that developed in Excel program. You start and calculate, and this is the link. If you have a computer, maybe I'll show you this again. You can download this file. This is just click, then you can get it. And using this tool, you can do the exercise. So we want to actually do some exercise later on in the afternoon. You can pick whatever exercise you want to do. I know some of you guys wanting to do emission modeling. Some of you wanting to have a traffic impact studies. So just imagine what you want to do and go through this Excel, and we'll probably discuss some level. And then most important thing is that when you see the recommendation, and you need to make sure that that makes sense to you. And you gotta have that capability of judging whether the tool actually gave you proper recommendation. This is a general procedure for applying simulation tools in the toolbox as well. Obviously, you have to identify what you want to work with. Depends on needs of HOV that kind of eliminates the planning tool. You want to have signal timing control. You want to do actuated or fix the timing plan, or you want to do some route guidance evaluations, and that actually gives you different needs for the modeling level. And also the purpose of studies, what kind of measures of effectiveness that you wanted to get, how much detailed information you need to get. If you are evaluating high-level benefit cost analysis, you only need to have a maybe delay measure or vehicle hour traveled for total network performance, which you don't have to do individual vehicular level evaluation. Or if you want to do calibration, do you have ways of getting the data for calibration? And what kind of data is available if you can actually easily do this? Budgets and other things are important. And also the many models are available. I have another set of slides showing existing simulation modeling tools, and some of them I did not even have tried it, but there's options available for open source to commercial softwares, and you probably want to have some understanding of strength and limitations, and efforts of needing to do the calibrations and other things. And you have to now evaluate out of your candidate models, and maybe cost is important. Can you do with the open source? Or if you want to publish your paper, you probably want to use the off-the-shelf commercial tool, widely accepted, versus a new open source tool never heard of. And data is actually available. You got them already, things like that. So you can select a model based on these criteria that you have developed by yourself. And then you collect the data, you do model calibrations, and you execute a model, and then you actually interpret the results of the simulation model. Again, how do you argue this is reasonable? If you can collect more data can actually reduce variability of the estimation. If you know the standard deviation of the estimate is the square root of n, right? So more n, it's not reducing by linearly, it's the square root of n is very slowly, but more data can help to have a better estimate. So you have more data, then it's better to do it. If you have not many data, just like I gave you the examples, we only had 1 day worth of data. Doing another day is just so expensive. So you'll have to justify how you can argue about it. Justify in a reasonable way, not making up. And then there might be anomaly results, and how do you deal with them? Again, I'm showing the results of those and exercise, and hopefully we'll exercise this and then see what happens. And you can do a lot of different things, and if you don't have a scenario, you can try this scenario. So if you want to do the ramp metering for some corridor study, and you have these settings that you can go through and click them, and it might give you a recommendation. So if you can think about ramp metering, what kind of tool do I need? Meso, micro, macro? Probably micro, right? And then what is you need, animation needed, and it probably tell you that you probably want to have off-the-shelf commercial software tools and so forth. So this is entering those inputs, and I'm going to just skip them. Maybe I can stop here. Let's stop here, if that's okay with you. We probably want to go back and then do this again. Any questions?
Sir?
Yeah.
The data for all 21 intersections was collected at the same time, same duration, or it was?
No, the internal intersections were collected almost at the same time of the study, but not the immediate 9 intersections, the near ones, we had to have rotating people. So we actually had students going around and collecting every 20 minutes. And external was collected at the same time as well. So the internal video and then entrance to the network were collected at the same time. But the middle of the intersections was rotating 20 minutes. I am not 100% sure, but that's what I recollect.
Maybe peak hour would have, like, something was taken care of that, or?
So again, this is the issue of variations. Locally, Chicago downtown, you might be surprised. Their signal timing plan was last updated in 1967. The reason is that this is a one-way street. There's not much change. So one-way street, all you need to do is maintaining speed. I don't know, you guys have a one-way street in India. If you actually hit the red every time you drive, it's because you are overspeeding. If you maintain speed limit, it's designed to get the signal on progression. So their issue is, so that's why we didn't optimize the green times and cycles. We only optimize offsets. And offsets are getting sort of outdated over the time, in part because of a number of cars moving, and those are affecting the offsets. Because when you have cars waiting a lot because of heavy demand, you actually have to have a queue clearance time. Because if there's no cars there, you hit the exact time. But if you have 3 cars from left turns and right turns waiting, you need to give 6 seconds to clear that up. So your offset changes. So that's how we actually did it. So in some sense, I am pretty confident that there may not have huge fluctuations in downtown Chicago, except for certain special events. Yes?
Sir, can this simulation tools be used for some policy interventions, proposed policy interventions which are at the city level or macro level? but the results we want to check for a micro level. For example, what is the change in speed of few corridors, for example.
So tell me about the policy you wanted to evaluate.
For example, area-based congestion pricing.
You need to have a lot of assumptions. So the congestion pricing will have even mode shift effect, and you'll have to assume those into different levels. So you might have a literature showing that X% of people switch mode depends on the pricing of the congestion. So it's not, I mean, simulation can do anything you want to do. The question is how do you generate those scenarios that are reasonable to what could possibly happen.
So mode choice analysis would be done before that. For example, I have
Sure.
developed a model,
Right.
and I want to simulate that model. It's a logistic model. In a simulation tool like this.
Yeah, simulation can do anything you want to do, as long as you provide the inputs and you calibrate and you collect anything you want to collect. But some challenges in the simulation is there's a HOV lane, and how do you model the violators? I mean, HOV, people actually do violate once in a while, and that's another interesting aspect. And if you have a HOT lane, and how do you model people who's actually paying for those tolls? I mean, in Washington, D.C., they have a beltway. Inside the beltway, they opened up the toll lane, and first day the toll went up to $34 per 6-minute route. So I mean, no one actually expected it. I mean, it's stable to about $7, $8 now, but it happens. But how do you actually expect that could happen? How do you model those is very, very challenging. So you gotta have a convincing argument about your scenario. Maybe literature can help. Any other questions? Okay, enjoy your lunch. Can we start a little bit early instead of 2, maybe 1:45?
We can start. Do they need to bring their laptops?
If they can bring, we can do this one.
Okay.
And then also I have an exercise for creating headway distribution,
Okay.
and they appreciate how a simulation is done.
Okay. So whoever is carrying a laptop, kindly bring it, and whoever does not have one, share with the person next to you. And we can get some laptops from our departments if you are really short.
And then they have internet access, I presume?
Yeah, they have internet access here. So then really come a little bit early. So we need to set up everything. So by 1:45 maybe if you can come now. That should be good.
Okay,
Okay.
thank you very much.
Thanks. Yes. You can leave your belongings here. You don't have to carry it with you. Even if it's a laptop, it's safe.
Oh, really?